So today we're going to do the second derivative test. This is the last unit before the midsection test. Okay, so first we're going to identify the relative extrema. So you should be able to do this just from looking. We have a max right here and we have a min right here. We know that the first derivative is equal to 0, right? The slope of the tangent line. And that's what we could put here for b. F prime of x equals 0. So we could say the first derivative is equal to 0. Right? The slope at this is right here, is flat. And then the second derivative, we know that for here, this is concave down, so the second derivative is negative. So, second derivative of x is less than 0, and here, the second derivative of x is greater than 0. Right, concave up. And concave down. So if you didn't remember, right, our second derivative tells us concave up or down. Or concave down. Okay, so to recap 5.6, we use the second derivative to determine concavity and points of inflection. So we would know that about like here, we'd have a point of inflection, right? When it switches from concave down to concave up. So we're gonna keep using the second derivative and we're gonna look at concavity. This lesson, we don't really care about points of inflection. In 5.7, we are going to use the second derivative to find mins and maxes. So we've done this before with like first derivatives, right? When we switch from like increasing to decreasing. Now we're doing it with the second derivative. So there's different layers of it. Alright, so looking back at our picture, we see our first derivative is 0 and we see that our second derivative is negative, and that gives us a max, right? So suppose that f prime of c is 0, then if the second derivative is greater than 0, then it has a relative minimum, right? If it's concave up. If it's concave down, then it has a relative maximum. So for me, it helps drawing it, because if I see that it's greater than 0, I might think, oh, that should be maximum. But once you draw it and you see that it's concave up, you can see that's a minimum. So this is the most important part of the notes. I always like to draw the concave up and concave down so I can clearly see, oh, this is a minimum or this is a maximum. Okay, so let's do our sample problems. So we have used the second derivative test to find the relative extrema of f of x equals x to the fourth minus 2x plus 2x squared. So we have two steps for these problems. Our first step is to find the first derivative, f prime of x, and set equal to 0. Right, our critical points, which we're really used to. And then our second step is plug in answers from step 1 into the second derivative. And then use the second derivative test. So it's not that bad. I think the hardest part is being able to differentiate between first and second derivative. But taking the second derivative usually isn't that bad. It's not like 3.6, we have to like plug it back in, the implicit differentiation. Okay, so let's look at this example. So the first thing that we want to do is find the derivative. So we have f prime of x equals, okay, so our first derivative is 4x to the third minus 4x. That's just a simple power rule. And then we're going to set that equal to 0. So take some time to figure out what those x values are. Alright, so you guys got it correct. We set this equal to 0. We pull out our greatest common factor, which is 4x. We're left with x squared minus 1. We know that this should be broken down. This is the difference of squares. So this can be broken down into 4x, x plus 1, x minus 1. And so we can see we have 3 zeros here. We have x equals 0, negative 1, and positive 1. So we figured out step 1. We got all of our critical points. And now for step 2, we need to plug it into the second derivative. So our second derivative would be, alright, you guys got it right. Our second derivative is 12x squared minus 4. And now all we have to do is plug in our points. And this is very similar to previous lessons. You can get the exact value, or you can just let me know if it's positive or negative. So you guys take some time to do that, and then we'll go over the different answers. So we want the second derivative of 0, the second derivative of 1, and the second derivative of negative 1. Right, very nice. This one's not so hard. We plug in 0. We can see 0 minus 4 is negative 4. We plug in 1. That's 12 minus 4 is 8. We plug in negative 1. Negative 1 squared turns back to positive. 12 minus 4 is again 8. So this one was easy enough to find the actual value, but the only thing we care about is the fact that it's negative, positive, and positive, right? And this is the second derivative, so we know that negative means concave down, positive means concave up, and this last positive obviously means concave up. So we can see that this is a max, a min, and a min, and so now we're going to write it like a script, right? So we say there's a relative min at x equals 0 because the first derivative at 0 equals 0 and the second derivative at 0 is less than 0, is negative. Sorry, this is a little tiny. So they're all similar, right? Relative max at x equals 1 because the first derivative of 1 is 0 and the second derivative at 1 is positive, greater than 0. And then the third one, almost exactly the same, but now replacing 1 with negative 1. Relative max at x equals negative 1 because the first derivative at negative 1 equals 0 and the second derivative at negative 1 is greater than 0. So this is the answer that we'd be looking for. Alright, good fix. See, I get messed up on this all the line. This is a max and these two are mins. So good catch. I see the negative and you think it's a min, but you gotta look at the drawing. So be careful, because clearly it's very easy to mess up. Alright, nice job. Our second example is, even though it's trig, it's not that bad. Okay, so first step, we need to find the first derivative. Alright, so the derivative for this, you guys got it right. This one looks weird because it's square root, but just remember, a number in front of a variable, just to the degree of 1, is just that number. So far our derivative is root 2, and the derivative of cosine is negative sine. It's already negative, so we're going to do plus 2 sine x. So that's our first derivative, and we want to set that equal to 0 to solve for x. So we have root 2 plus 2 sine x equals 0. Move the root 2, so we have 2 sine x equals negative root 2. Divide by 2 on both sides. Sine x equals negative root 2 over 2. So we want to think to ourselves, where on the unit circle does sine equal negative root 2 over 2? Alright, we got it correct. So there's 2 spots where this is true. It's in quadrant 3 and quadrant 4. So we have 7 pi over 4 is one spot, and 5 pi over 4 is the second. So these are our 2 critical points for step 1. And now for step 2, we need to find the second derivative and plug that in. So we have our second derivative. This root 2 just goes to 0 because any constant, just the derivative of a constant is 0. And the derivative of sine is back to cosine. So I'm sure you noticed there's like a pattern where sine and cosine keep flip-flopping with the signs being changed sometimes. So that's really normal to just keep taking the derivative and it goes back and forth. Okay, so now we need to plug it in. So we have the second derivative of 5 pi over 4 and the second derivative of 7 pi over 4. So take a second to try and calculate those values. If you don't want to calculate the value, you can just tell me if it's positive or negative. Alright, so if we plug this in, 5 pi, we're looking for the 2 times the cosine of 5 pi over 4. So this is the x value. So if I'm looking over here, the x value is negative root 2 over 2. So we have 2 times negative root 2 over 2. The 2's cancel, we're left with negative root 2. Even if you couldn't remember exactly where this was, even if you just knew the quadrant, that would be helpful, right? Because quadrant 3, we know that both the x and the y are negative. So this is a negative number times a positive number. It has to be negative. 7 pi over 4, 2 times positive root 2 over 2 equals root 2, which is positive. So, right, we have a negative, which is concave down, positive, which is concave up. I'm going to try not to mess it up this time. So we have a relative max at x equals 5 pi over 4 because the first derivative of 5 pi over 4 equals 0, and the second derivative at 5 pi over 4 is less than 0. And then we have a relative min at x equals 7 pi over 4 because the first derivative at 7 pi over 4 equals 0, and the second derivative at 7 pi over 4 is greater than 0. So this is our beautiful little scripted answer. So the super cool thing about calculus is that you can do all of this without a calculator. But just to give you some context, I'm going to show you what this looks like on the calculator. So be really careful when you're plugging this in. We have the square root of 2, but you have to make sure you push over to the right or else the x is going to be, the x should be like not in that square root. So just be careful. 2 cosine x. Oh, also I forgot to mention, they gave us the interval of 0 to 2 pi. So that's why we only did 5 pi over 4 and 7 pi over 4. Right? We could have kept going on. We could have done another loop in the circle and come back around, but they only wanted us to look at one loop in the circle. So when we're putting that in the calculator, we can go from 0 to 2 pi. If you type in 2 pi, it'll give you the decimal automatically. So let's take a look at the graph. Oh, this thing is graphing slow. Okay, so if we look at this, we can see, let's see if I can put this center. We can see that we have a max here and a min here, right? And that's what we found. We found a max at 5 pi over 4 and a min at 7 pi over 4. And then let's do the first one. Okay, so I'm going to give you like a hack or whatever. If you're allowed to use your calculator, you can use it, right? I want to find the relative extrema. I could do this without calculus, right? So let's say I completely forgot what was going on. I plug in the graph just so I can see what it looks like. I'm going to set my window to negative 10, 10, negative 10, 10, just because that's a good point. I graph it. Okay. I'm going to zoom in just so I can see it a little better. Okay, so even without calculus, I know that there's two minimums and a maximum, right? I could literally trace it, zoom, and do my maximum. And I could see, like, it is, I mean, that's essentially a 0. Something in the negative 6. So I have 0, 0. And then let's do a minimum. And I can see that's 1, right? So when you're super stuck, you can use your calculator, but you can't just say maximum at 0, minimum at negative 1 and 1. You have to show me the calculus. So when you're using your calculator, you can like figure out what's going on and then work backwards with the calculus, but I need to see the calculus. So just a hint when you're super stuck, because if you're allowed to use your calculator, which you are in most of my quizzes and tests, then use it, you know? So that's proof, right? We did this all without a calculator. And people developed calculus before there was graphing calculators, right? But you guys had the benefit of using it. So feel free to check your answer, right? If you see that it's wrong, if this little box is not matching your graph, then go back and check it because you did something wrong. All right, last example. If there is only one critical point, and that critical point is a max or a min, then it is an absolute extremum or max or min. So if there's only one point and it's a max or min, then by default it's an absolute max or min, right? Like if there's only one child, you're the oldest child by default and the youngest. Okay, so this derivative is really icky, but it's not that bad. So we can see that it's product rule. So we're going to have f is x, negative x. We're going to have g is e to the x over 4. And then the derivative of negative x is, alright, so the derivative of f is going to be just negative 1. Derivative of g is going to be the same thing times our product rule times 1/4, right? Because you could write this, right? You could write this e x over 4. You could also write as e to the 1/4 times x. And then it's easier to see that you need to do chain rule and multiply by that 1/4. So we're going to cross that in our product rule. We get negative x over 4 times e to the x over 4 minus e to the x over 4. I know it's super ugly, but this is a legitimate equation that you could be asked to derive. Alright, so this is our first derivative. We need to set them equal to we need to set it equal to 0 to solve. So we have negative x over 4 e to the x over 4 minus e to the x over 4 equals 0. I'm going to pull out an e to the x over 4, actually a negative. Negative e to the x over 4. We are left with x over 4 plus 1 equals 0. I pulled out negative so that this inside thing would look a little prettier. But you could have just pulled out a positive e to the x over 4. This is going to be, this one you can't make equal to 0 because no matter what, like a number to anything is never going to be 0. So we just have to worry about this factor right here. So we set that equal to 0. X over 4 plus 1 equals 0. Move the 1. X over 4 equals negative 1. X equals negative 4. So all that gross work, we actually just found out right here. This is our critical point and our only one, right? Now the tricky part is the second derivative. Okay, so this looks really gross to derive, but something that we want to take note of is that we've actually sort of done it all. So if we look at this first part right here, This is very similar to the original equation. The only thing is that it's divided by 4, right? This is negative x times e to the x over 4. This is negative x divided by 4 times e to the x minus 4. So when we're trying to find the derivative of this thing, all we have to do is take the derivative of the original equation and divide it by 4. So if I take this whole guy and divide it by 4, that's our first part of our derivative. So we have negative x over 16 e to the x over 4 minus 1 over 4 e to the x over 4. So the derivative of this chunk is this chunk. And now we just need to subtract the derivative of this chunk, which we actually did over here. So we're just going to do minus 1/4 e to the x over 4, right? So even though this derivative looks super gross, it was really just doing stuff we already did. If you wanted to, you could redo the product rule, but you sort of want to see the shortcut that like you already did a lot of the work. The only thing that was different was that we had a coefficient. We had a coefficient of negative 1/4, or 1/4. That's the only difference. Alright, so this is our new derivative. Let's simplify it. So I'm going to pull out negative 1/4 e to the x over 4, because that's something they all have in common. We are left with positive x over 4 plus 1 plus 1. And now we need to plug in our negative 4. So if I have f second derivative of negative 4, I have negative 1/4 e to the negative 1 all over negative 1 plus 1 plus 1. This equals negative 1/4 e to the negative 1 times 1. So you could put this in your calculator. If you wanted to rewrite it, you could do it without a calculator. You could do negative 1/4 times 1 over e times 1. I don't really need to know what this is. I know that it's negative because it's a negative number times a positive number. But if you want to, you could just put in your calculator and figure it out. But I know that this is negative, so it's concave down, and my script will be absolute. Remember, from this thing up here, we know that it's absolute because there's only one. Absolute max at x equals negative 4, because the first derivative at negative 4 equals 0, and the second derivative at negative 4 is less than 0. So while you're writing that, let's look at it at the graph. Negative x e to the x divided by 4. We have this graph. We can't fully see. Let me change the window to negative 6. Sort of hard to tell, but we have a max right here. And we know from all our work that it's a max at negative 4. So, again, we checked it and it worked. So, the hardest part about this problem is obviously the second derivative. But the concept is the same. Hopefully the second derivative test makes sense. And that's it.